Alright guys, so I want to talk about the normal distribution. This is one of the distributions that are pretty common in nature. Um, from the distribution of student scores to a pile of mud, a lot of things are in fact distributed normally. And this is a specific shape, and it's also evident here. This is a specific shape where it kind of bulks around a particular center, and then there is some variability as we go away from the center, and the curve tends to taper down as we move away from the central value. So this is pretty much what a normal distribution shape looks like. What we want to look at in this video is, why does this shape look like this? What does it represent? And is there a way to analytically see or formulate this shape? Okay, so for that, I'm going to go ahead to the Transoms online graph plotter. Now we're going to start with the y equals x line. Remember, this is a line, a shape, or any curve. It is going to have an equation. And I have a y equals x equation. This is what it looks like. It's a line, right? Let's look at y equals x squared. This purple curve has a smiley face, right? And then it extends above on both sides. But if you add a negative sign to it, then this becomes a sort of a sad face, right? It inverts. So, so that's just something that one small intervention in the equation kind of totally changes the way it looks. And we're trying to head towards a specific shape. We're trying to find this specific normal distribution shape, and it looks pretty much like this negative x square, right? But that's not exactly what it is, and that leads us to a very special family of functions, these exponentials, right? So let's look at how y equals e to the power x looks like. It looks like this. So it's an exponential. It's continuing all the way, increases exponentially. And then the e to the power minus x is a negative exponential, right? So it's decreasing. But let's use what we were trying to work with, the x squares. Remember, the x squares were a smiley face, but look, the negative x squared was something that was close to the normal distribution, right? But if we put this negative x squared as a power of the exponential, it tends to look exactly what we were looking for, the normal curve, the normal distribution, right? Uh, there's not much difference between this and this 0.5 coefficient in the power of the exponent. This black line and the purple line. The black line tends to taper rather slowly than the purple one, but the reason we're so interested in this specific black exponential powered, the one with the zero point 0.5 coefficient, is because um, this is a more realistic formulation of the normal distribution, and also when with this coefficient, with this factor, this is integrated, we can ensure the area under the curve to be a particular value, and that makes it more useful, and we'll see in just a bit. But before we get down to that, what I want to do next is introduce some more variations in this. So for example, if you look at line this equation 9, it is the same as equation 8. I'm only subtracting a 0 and dividing it by 1 and then squaring it. So it's the same thing. It still turns out to be x squared, but this is just one way to write it. The reason I do that, it doesn't change the shape of the curve. The blue kind of overrides the black one, so it's the same thing. But the reason I do that is because I want to be able to, let me add one more expression here. The reason I do that is because I want to show that if I subtract a particular value, for example, if I subtract 2 from this, I'm able to move the center of this curve from 0 to 2, and let's just make it 1. Then I am um, having the center at 1, right? So whatever I set here is in fact the center of this black curve. So in a way, what I could do is I could center my curve based on this specific value, and you could relate this at some point that this is in fact the mean or the central value of this normal distribution. So we could always have our distribution centered around a particular value. The only mechanism that we would want to take care of is to ensure that we set up this specific number, and that's where this distribution is going to be centered at. Another thing that is super interesting is this specific factor. Remember, we divided this by 1, but if we switch that to something else, we're able to, in fact, let's make this back to 0. Let's turn this off, and let's zoom up a bit. Yeah, so remember, when we change these values, you could notice what's going on. You could notice something. As I increase this particular value, what I see is, let's have both of them on. Let's set this to 0.45. Let's just compare this with the one in the denominator for the blue one. Now notice the difference. This black curve tapers down rather quickly. So I'm able to control the spread of this distribution by playing around with this specific value in the denominator, which is the standard deviation for this normal distribution. Now we've kind of looked at two metrics here. Where do we center it? The mean, which is this particular number, and how quickly it tapers off. The deviation from the central value called the standard dev, which is this number in the denominator. So these are the two metrics that we've used to characterize our normal distribution curve so far. Now let's look at their effect in a simulation. For example, we could always, but before we do that, notice inserted an additional factor, this 1 over square root 2 pi. This is that factor when multiplied with the normal distribution curve, and then when this is integrated. Now notice this is an equation, y equals this factor and then the exponential with this factor in the power. Since this is an equation, if I integrate this equation to find the area under this curve, that turns out to be 1. And this is a super important property for the normal distribution because it allows us to connect it with probability. And if we look at a normal distribution graph such as this, notice what's really signified here from within one standard dev. Notice this interval from within -1 standard dev to +1 standard dev. We are in fact capturing 68% of the data within 1 standard deviation from the mean. Within the 2 standard deviation interval, we are looking at 95% of data within this interval, right? So that's 95% of the data within our interval. So since this is a percentage, it's out of 100, or we could interpret it in terms of probability out of 1. This makes this special curve super useful for interpretation because now we could model our data in this normal distribution, and then we could calculate probabilities based on the areas that get occupied within certain intervals or ranges, right? So one way to now, let's just call this M and add a slider to this. M is the mean, right? And let's just call this as an S for the standard deviation. Now this S is out of this square root, and let's just add the sliders for both of them. Let's vary the mean from -3 to 3 in steps of 0.01, and let's move the standard deviation from 0 to, let's just say, 0.8 within steps of 0.01. Right, so let's see how this behaves first in terms of the standard dev. right? So let's have it, and let's set the mean to 0. Okay, so now this is centered at 0. Hold on. Okay, now this is centered at 0, and as we see the movement of the standard dev from 0 to 0.8, we see how the spread varies, right? So let's just stop it at some point, and let's also visualize the movement of the mean, right? So this moves from 3 to -3. Notice the value of m that's being taken in this expression right here. So in a nutshell, we are able to characterize a standard deviation, and we could visualize its expression, which looks pretty much like this. It is in fact this, and it can be characterized by two key metrics, the mean and the standard dev, which appear here in this equation. And an important observation is that this factor allows us to quantify the area under this curve as 1. In summary, this is what it is. This is the mean and this is the standard deviation, sigma. This is the overall expression which we just implemented, and this factor is in a sense ensuring that when we integrate this equation, the area turns out to be 1. Uh, the area under the curve turns out to be 1.